Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin. Far from the bright inner planets, the solar system is enclosed by a broad moving environment, shaped by the sun itself. The sun releases a steady flow of charged particles, mostly protons and electrons, called the solar wind. This wind carries the sun's magnetic field outward, forming an expanding bubble that surrounds the planets and extends far beyond the orbit of Neptune. That bubble is the heliosphere. It is not a rigid shell. It is a dynamic region whose outer boundary shifts with solar activity and with the pressure of the thin interstellar medium outside. Yet it serves as a practical frame for the outer solar system, because inside it, the solar wind and the sun's magnetic influence define the background conditions that any small body passes through on its way inward. In these outer distances, sunlight is weak. The energy arriving at a surface drops rapidly with distance from the sun, and temperatures remain low enough that many substances stay frozen and stable. A small body can travel for long periods with little visible change. If it carries volatile ices, meaning substances that can turn to gas when warmed, those ices can remain locked in place beneath a surface layer. The outer solar system is therefore a region of preservation and quiet motion, where gravity is the dominant force, shaping trajectories, and where the signals available to observers are faint. When an object is first detected at the edge of survey sensitivity, it is not yet known as a physical body with a described surface. It is first known as a moving point of light measured against a background of stars. The heliosphere sits within an even wider setting. Outside it lies the interstellar medium, the sparse gas and dust that fills the space between star systems. The density is extremely low, yet over long times it can still matter for surface processing. Cosmic rays and ultraviolet radiation can alter surface molecules, darkening and chemically transforming exposed layers. Dust impacts, though rare, can slowly sandblast and modify surfaces. These influences operate over spans far longer than a single observation campaign, but they shape the condition in which an object arrives. A body that has traveled between stars may carry a surface that has been processed for a very long time, or it may have been renewed by fractures or by earlier heating events in another system. At this stage, the details are unknown. What can be held is the environmental frame, cold, sparse space, with sunlight increasing as the object approaches the sun, and with the solar wind providing a steady particle flow that can later shape any ionized outflow. Within this broad outer region, the paths of small bodies are set mainly by gravity. The sun's gravity acts across vast distances and still dominates the motion. The pull is weaker far out, but it is persistent. The giant planets add their own gravitational influence not as constant pulls from fixed points, but as moving masses that can perturb a trajectory if an object passes near them. Jupiter is especially important because of its mass. A close passage can bend an orbit, altering the object's future path and speed relative to the Sun. Even without an extremely close encounter, Jupiter can introduce measurable changes if the geometry aligns. In the earliest stages of tracking a faint object, these planetary influences must be included in orbit models because they can affect predictions and because they can make an orbit solution sensitive to small uncertainties. Sunlight contributes another influence, though smaller than gravity, by carrying momentum. When photons strike a surface, they exert a small pressure. This radiation pressure can gently push on small particles, and in special circumstances, on very small bodies with large surface area relative to mass. For typical kilometer-scale objects, radiation pressure on the nucleus is negligible for orbital motion. But radiation pressure is crucial for dust grains released into a coma because it shapes their paths and produces tails. At this outer distance, dust release may be weak or absent, but the mechanism is part of the environmental frame. If dust is released, even in small amounts, sunlight can sort grains by size and push the smallest grains away from the sun more rapidly. The phrase "doing something astronomers rarely see" can apply in the outer frame in a quiet and technical sense. Rarely seen does not have to mean physically impossible. It can mean that the object becomes detectable at an unusually early stage, or that it presents an orbit geometry that is uncommon among known small body populations, or that it appears to show hints of activity farther from the sun than is typical for most observed comets. It can also mean that an object's classification, whether it is bound to the sun or not, becomes apparent in a way that stresses the limits of survey detection and orbit fitting. Rarity in astronomy often arises from selection. Many objects pass unseen because they are too faint, too fast, or in parts of the sky that surveys do not cover as deeply. When one is found, it can represent a special intersection of object properties and observing conditions. At the outer edge, the first measurable properties are therefore simple ones. There's a direction in the sky. There's a rate of motion across that sky. There's an apparent brightness in one or more filters. Each of these has uncertainty. Each is influenced by the environment, both physical and observational. If the object is faint, the measured position may shift slightly, depending on noise and on the accuracy of the star catalog used for reference. If the object is moving quickly, it can trail in images, complicating centroid measurement. If the object is near the Milky Way on the sky background, stars can crowd the field, making detection and measurement harder. These factors can make early orbit solutions uncertain, and uncertainty can give the impression of behavior that changes from night to night, when what is changing is the fit's confidence. The outer environment also sets the conditions for the onset of activity. If the object contains very volatile ices near the surface, such as carbon monoxide ice, it can begin sublimating at large distances where water ice remains stable. If activity begins, it can produce a faint coma. A coma is a cloud of gas and dust surrounding the nucleus. At great distance, a coma can be so thin that it is difficult to see in survey images. Yet even a faint coma can affect brightness measurements, and if the outgassing is asymmetric, can create a small thrust that perturbs the orbit. At this stage, these are possibilities within the environmental frame. The strongest statement is that the outer solar system is a region where such effects are subtle and where detection is difficult. The heliosphere's particle environment adds another quiet influence. If gas is released and becomes ionized by sunlight, it can interact with the solar wind and be drawn into structures shaped by magnetic fields. This process can create ion tails, which can shift rapidly with solar wind changes. For a faint, distant object, an ion tail may not be detectable. Yet the environment exists regardless of detection. It is part of the physical context that will later shape what is visible if activity grows. In this first section, 3I Atlas is held as a traveler entering a structured but subtle region, cold space, within the heliosphere, under the steady guidance of solar gravity, with sunlight as both a measuring beam and a heating source. The rarity, if it exists, begins here as a combination of detectability and trajectory. The object is not yet described in terms of detailed surface behavior. It is framed by the largest scales that still matter, the sun's expanding influence, the boundary, with interstellar space and the quiet physics that governs motion and sets the stage for the first faint signals to be collected by surveys. The moment 3I Atlas enters human records is not a moment in space, but a moment in data. A survey telescope images a patch of sky, then images it again later, and software searches for small changes. The sky in such images is crowded. It contains stars at many distances, unresolved galaxies, and the constant imprint of noise from the detector and from the atmosphere. A moving object is identified not by its appearance alone, but by a pattern, a point that shifts consistently between exposures. This is the discovery pipeline, a chain of steps designed to find faint motion reliably and to reject false motion created by artifacts. The first stage is exposure. A wide-field survey chooses an exposure time that balances depth and trailing. Longer exposures collect more light from faint objects, but also allow a fast mover to smear across pixels, reducing detection efficiency and making position measurement less precise. Shorter exposures reduce trailing, but may miss faint objects altogether. Surveys like Atlas are designed for cadence, revisiting the same sky regions to catch moving points. Cadence matters because it allows linking. One image can contain a transient noise fluctuation that looks like an object. Two or more images can test whether the signal repeats at a consistent offset. Linking is the process of associating multiple detections as the same object based on plausible motion. This linking is probabilistic. It uses expected ranges of motion for near-Earth objects and for more distant bodies. For an object that is distant or that moves with an unusual apparent rate, linking can be more difficult. The software must search a broader parameter space, and false associations become more likely. Therefore, discovery is not only about the object, it is about how well its motion fits within the survey's designed search patterns. Once a candidate tracklet is formed, the survey reports positions and brightness to central repositories that coordinate minor planet data. Each report includes a time, a sky coordinate, and an estimate of brightness in the survey's filter. The position is tied to a star catalog. The brightness is tied to calibration stars in the field. Both carry uncertainty. In particular, faint detections can have position errors that are larger than the nominal precision and brightness errors that can be substantial. These early measurements are still valuable because they start the orbit determination process. They are also fragile because any systematic bias, such as a small timing error or a slight distortion in the image geometry, can propagate into the preliminary orbit. A preliminary orbit is computed from a short arc of data. A short arc is a limited span of time over which the object has been observed. With a short arc, many different trajectories can pass through the same set of sky positions because distance is not well constrained. This is especially true for distant objects because parallax is small. Earth's motion provides parallax, and parallax helps determine distance, but at large distance the parallax shift is subtle. Therefore, early orbit solutions can shift significantly as new data arrive. This shifting can be mistaken for the object changing behavior when it is actually the solution converging as the observational arc grows. Follow-up observations are then requested. Larger telescopes can observe fainter objects and measure positions more precisely. The goal of follow-up is not only to see the object again, but to anchor its motion. Each additional astrometric point reduces uncertainty. The most valuable follow-up observations are those that extend the time baseline because they add leverage. A measurement taken days or weeks after the initial discovery can constrain curvature in the motion and distinguish between competing orbit families. Follow-up also checks whether the object is real and persistent. Survey detections can sometimes link artifacts or variable stars into false moving sources. A real object will appear again where the orbit predicts. In this stage, the phrase "doing something astronomers rarely see" can attach to the discovery pipeline itself in a specific way. Rarely seen can mean that the object is detected at an unusual distance for its brightness, which can happen if it is large, reflective, active, or simply observed under exceptionally good conditions. It can mean that the object's apparent motion does not match the most common distributions for nearby asteroids, prompting special attention. It can also mean that early orbit fits suggest an unbound trajectory, quickly making it a candidate interstellar object, which are rare in the observed record. The rarity is then a statistical rarity in the dataset, not a physical impossibility. Brightness at discovery is often misread as a direct indicator of size. In fact, brightness is a compound measure. It depends on size, albedo, phase angle, and any contribution from dust. If the object is active, dust can increase the scattering area dramatically, making the object appear much larger than the nucleus. If the object is inactive but has an unusually high albedo, it can appear bright for its size. Without additional information, early size estimates rely on assumed albedo values, often typical for comet nuclei or for certain asteroid classes. This produces a size range, not a single answer. If the object later turns out to have a coma, the size range must be revised. This revision can look like changing estimates and can feed the sense of unusual behavior. In reality, it is the correction of an early assumption. The discovery pipeline also involves quality control. Measurements from different observatories can disagree slightly because of different optics, different detectors, and different reduction pipelines. Some observatories may report positions that consistently fall on one side of the predicted path, creating systematic residuals. A careful orbit determination process accounts for this by weighting data based on estimated precision and by rejecting outliers when justified. Outliers can occur from misidentification, from poor seeing from contamination by nearby stars, or from tracking errors. The goal is to build an orbit that is consistent with the best data and that yields residuals consistent with expected measurement errors. If the object is faint, its image can be influenced by background. A faint galaxy or star can blend with it, making it appear brighter and shifting its measured centroid. As it moves, the blend changes, creating spurious variability and spurious astrometric shifts. This is one reason surveys prefer multiple observations and independent confirmation. When several observatories see the object under different conditions and still obtain consistent positions, confidence grows. In the earliest days after discovery, the object is therefore less a physical entity than a data product with growing definition. Its identity stabilizes through repeated detection. Its orbit stabilizes through accumulated astrometry. Its brightness behavior stabilizes through calibrated photometry. If at any point the early data suggest a path that is difficult to reconcile with a bound solar system orbit, the object receives extra attention and the follow-up network intensifies. This is a normal process, not a sign of extraordinary physics. It is the community responding to an outlier in the data space. 3I Atlas in this region is best described as moving from uncertainty to constraint. The survey pipeline catches a faint moving point. Follow-up anchors it. Orbit solvers test competing trajectories. Data services integrate reports. At each step, the rarity lies in the combination of faintness motion and inferred orbit class. Astronomers rarely see certain combinations because surveys have limits and because the population of objects that meet those combinations at the right time in the right part of the sky is small. The object does not need to behave strangely for it to be rare in the dataset. It only needs to sit at the edge where detection linking and orbit fitting become difficult, and where careful measurement begins to replace early uncertainty. As the discovery reports accumulate, the scattered points on the sky become a coherent track. In this region, the focus stays with that track, and with the disciplined transformation from sky positions into a preliminary orbit. Every measurement is a line of sight from a particular place at a particular time. The object's true position in space lies somewhere along that line. The act of orbit determination is the act of finding the three-dimensional trajectory that makes all those lines of sight intersect a single moving body under the influence of gravity within the uncertainties of measurement. The first practical tool is astrometry, the measurement of precise sky coordinates. Astrometry depends on reference catalogs that map the positions of stars with high accuracy. An image is calibrated by matching stars in the field to catalog entries correcting for optical distortion and for atmospheric refraction. Then the object's centroid is measured. For a faint source, the centroid is not a sharply defined point. It is an estimate derived from a blurred light profile. Noise and background variation shift the estimate slightly. Therefore, astrometric points come with uncertainty, and that uncertainty is not always perfectly represented by formal error bars. The reduction pipeline can underestimate or overestimate errors depending on conditions. With a set of astrometric positions, an initial orbit can be computed. In the early stage, when only a short arc is available, orbit solutions can be degenerate. Degenerate here means that different combinations of distance and velocity can produce similar sky plane motion. For distant objects, parallax is small, and the sky track can appear nearly straight over days. This allows multiple orbit families, some that are bound long-period orbits, some that are slightly hyperbolic, some that differ in inclination or perihelion timing. The solver chooses the solution that best fits the data given a dynamical model, usually including the Sun and major planets. The result is a best-fit orbit with uncertainties. The uncertainties can be represented as a covariance capturing how errors in one parameter correlate with errors in another. These correlations matter because they determine how predictions widen over time. Orbit predictions are expressed as an ephemeris, a list of predicted sky positions at future times. Follow-up observers use the ephemeris to point telescopes. If uncertainties are large, the predicted region can be wide, and finding the object again becomes harder. This can lead to a feedback loop. The object is hard to recover because the orbit is uncertain, and the orbit stays uncertain because recovery is hard. Surveys and follow-up networks break this loop by prioritizing early re-observation when the uncertainty region is still small. As the arc lengthens, the object's apparent motion shows curvature. Curvature comes from two sources: the object's gravitational acceleration as it approaches the Sun and the changing geometry of observation as Earth moves. Measuring curvature allows the solver to determine distance more precisely and to separate the object's true motion from perspective effects. This is when the orbit begins to stabilize. Stabilization does not mean the orbit stops changing. It means that new data refine parameters rather than overturn them. A stable orbit solution yields predictions that become increasingly accurate, enabling more consistent follow-up and deeper studies. The phrase, "doing something astronomers rarely see," can connect here to the nature of the orbit solution itself. If the best-fit orbit is strongly hyperbolic in a barycentric frame, it indicates an interstellar trajectory. Such objects are rare in the observed record because they are difficult to detect and because the time window for observation is limited. If the hyperbolic nature is only marginal, the orbit may sit near the boundary between bound and unbound, making the classification sensitive to small changes in the data. This sensitivity can be perceived as unusual behavior because each update may shift the eccentricity and the inferred asymptotic speed. In reality, it is the mathematical expression of limited data and the object's particular geometry. Reference frames are central. A heliocentric orbit is computed relative to the Sun, but the solar system has a barycenter, a center of mass, that shifts due to planetary motion. For classification of bound versus unbound, barycentric elements are often more stable, especially at large distances where the influence of planetary motion relative to the Sun can bias heliocentric interpretations. An object can appear more hyperbolic or less hyperbolic, depending on the frame and on whether a close planetary perturbation has occurred. Therefore, careful classification examines the inbound barycentric solution, not merely the heliocentric fit at the time of observation. Residuals provide the health check. After fitting an orbit, the solver computes residuals for each observation. A good fit yields residuals that are small and randomly distributed around zero. If residuals show a consistent pattern, the model may be missing something. The missing element could be a systematic error in some subset of data, such as a timestamp offset or an astrometric bias in a particular pipeline. It could be unmodeled physics, such as non-gravitational acceleration due to outgassing. At this stage, the responsible approach is to test the data first. Different weighting schemes can be applied. Outliers can be removed if justified. The fit can be rerun. If the pattern persists, then additional terms can be introduced. A key risk for faint-moving objects is centroid bias from extended light. If the object has a faint coma, the measured center of light may not coincide with the nucleus. If the coma is asymmetric, the centroid can shift along the tail direction. This can create systematic residuals that mimic a dynamical acceleration. The effect can be subtle at the level of fractions of an arcsecond, but over weeks it can produce a persistent offset. Therefore, when residual patterns are seen, observers check whether the object appears stellar or slightly fuzzy, and whether the measured position depends on aperture choice or image processing. High-resolution follow-up can reduce this ambiguity. Another observational challenge is trailing. If the object's apparent motion is fast, it can trail in exposures. Trailing spreads light along a line, reducing peak brightness and altering centroid measurement. Some pipelines correct for trailing by fitting a trailed point spread function, but not all do. If trailing is not modeled well, astrometric errors can become systematic. This again can mimic dynamical effects. Therefore, orbit determination must be paired with understanding of observing conditions. In this region, the orbit is not yet a story of materials or chemistry. It is a story of geometry and of statistical inference. 3I Atlas becomes a trajectory through space expressed as elements and uncertainties refined by each new night of data. The rarity, if present, is a rarity in this dynamical space, a track that either is clearly unbound or sits near the boundary in a way that tests the resolution of current surveys. The careful description is patient. It notes that orbits converge as arcs lengthen. It notes that residuals can reflect both physics and measurement. It holds classification as a conclusion that strengthens with time. By the end of this section, the object's path is no longer merely a sequence of points. It is a computed orbit that can be used to predict future positions and to plan further observations. Its uncertainties are quantifiable. Its residuals can be inspected. The foundation is now set for the next layer, where apparent speed and approach geometry are separated from true space velocity, and where the orbit's character becomes a clearer part of the measured identity of 3I Atlas. Once the orbit is established in preliminary form, attention turns to how the object approaches what its motion looks like from Earth, and what its motion truly is in space. This distinction matters because the phrase "doing something astronomers rarely see" can easily attach to apparent speed, and apparent speed can mislead. A point of light can cross the sky quickly because it is very close, because it is truly fast, or because the geometry of observation makes its angular motion large. Conversely, a truly fast object can appear slow if it is distant, or if its motion is directed mostly toward or away from Earth. In this region, the focus stays with approach geometry and with the careful separation of sky plane motion, Earth relative motion, and Sun relative motion. The most immediate measure is angular speed, the rate at which the object's position changes in the sky, often expressed in arcseconds per unit time. This is a two-dimensional projection. It depends on the object's distance from Earth and on the component of its velocity, perpendicular to the line of sight. If the object is close, a modest physical speed can produce a large angular speed. If the object is far, even a high physical speed can produce a small angular speed. Therefore, angular speed alone cannot determine the object's energy or origin. It is a tool for detection and tracking, and it influences the choice of exposure times, but it is not a classification measure. To understand true motion, astronomers reconstruct the object's heliocentric and barycentric velocities. The heliocentric velocity is the velocity relative to the Sun. The barycentric velocity is relative to the solar system's center of mass. These velocities can be decomposed into components: the radial component, toward or away from the Sun, and the transverse component, perpendicular to that. The heliocentric speed changes as the object falls inward under gravity. Even a bound object starting from a distant orbit speeds up near perihelion. An interstellar object begins with a non-zero asymptotic speed relative to the Sun, and gravity adds to that as it approaches. The key quantity that distinguishes interstellar from bound is not the heliocentric speed near the Sun, but the excess speed at large distance after removing gravitational acceleration, the velocity at infinity. That quantity is derived from the orbit's energy and becomes stable only when the orbit is well constrained. Approach geometry includes the direction of arrival relative to the ecliptic plane. The ecliptic is the plane of Earth's orbit. Most known asteroids and many comets have orbits near this plane because the solar system formed from a disk. An object arriving on a steeply inclined orbit can therefore appear unusual in a statistical sense. A high inclination changes how the object moves through the sky and which surveys are likely to catch it. Surveys often concentrate near the ecliptic, where the density of minor planets is highest. A high-inclination object may be detected later or under different observing strategies. If 3I Atlas is on an unusual inclination, its discovery and follow-up pattern can differ from typical cases, contributing to its perceived rarity. Another geometric factor is elongation, the angle between the object and the Sun in the sky. Elongation determines visibility. When an object is close to the Sun on the sky background is bright and ground-based telescopes often cannot observe it. Objects near conjunction can be lost to follow-up, even if they are intrinsically interesting. When elongation is large, the object can be observed in a dark sky. This affects how quickly the observing arc can grow and how stable the orbit becomes. An object that happens to be discovered at a geometry that keeps it observable for long stretches will accumulate data, quickly refining orbit and revealing subtle effects. An object discovered near a geometry that soon becomes unfavorable may remain uncertain longer, and the orbit may appear to change more with each new data point because each point carries more weight. Phase angle. The Sun object-observer angle is another geometric factor that affects brightness and therefore influences how speed and motion are perceived. At certain phase angles, dust can produce strong forward scattering, making the object appear much brighter than expected. A brighter object is easier to measure astrometrically, yielding better orbit constraints. But brightness changes driven by phase angle can also be misread as changes in activity. Therefore, geometry must be accounted for before linking brightness evolution to physical changes. Earth's own motion can create apparent reversals in sky-plane motion. As Earth orbits the Sun, it can overtake or be overtaken by an object in projection, producing retrograde loops in sky coordinates. This effect is common and does not mean the object reverses direction in space. For a newly discovered object, this can affect linking and orbit solutions because apparent motion changes over weeks. Orbit determination models include Earth's motion, but the observer's intuition can still be misled by apparent changes. A careful description keeps the distinction clear. The object follows a smooth trajectory under gravity, while the sky-plane projection can behave in ways that seem complex. If astronomers describe something rarely seen in relation to approach, one grounded reason could be a combination of high inbound speed and an observation window that still allows substantial tracking. Interstellar objects, by definition, do not return, and their time near the inner solar system can be limited. If one is detected early and tracked over a long arc, it becomes a rare data set rather than a rare physical process. Another grounded reason could be an approach direction that makes the object visible at night for many weeks, allowing unusually dense monitoring. Another could be an approach geometry that brings it near a major planet, creating an opportunity to measure perturbations and to test orbit models in a sensitive region. Approach speed relative to Earth also matters for observational strategy. A fast Earth-relative approach increases apparent motion and can complicate spectroscopy because the object moves during exposures. It can also create larger uncertainties in photometry if trailing is not corrected. Yet a fast approach can also bring the object closer, increasing brightness and enabling more detailed study. Conversely, a slow Earth-relative approach can keep the object in accessible skies longer, but at greater distance, limiting brightness and reducing spectral opportunities. These trade-offs shape what is observed and therefore shape the narrative of rarity. In this region, the most accurate language treats speed as a set of related quantities: angular speed on the sky, heliocentric speed, barycentric speed, and asymptotic speed. It treats geometry as the arrangement that maps one quantity into another and that determines observability. It also treats the label rarely seen as emerging from selection. An object can be physically ordinary yet rare in observation because the geometry of its arrival and the timing of survey coverage align in an uncommon way. The object can also be physically interesting, but the first step is always to describe what the geometry implies before moving inward into the deeper physical interpretations. By the end of this section, 3I Atlas is framed by a clarified approach. Its apparent motion is understood as projection, its true velocity is understood through orbit energy, and its visibility is understood through elongation and phase. The stage is then prepared to examine the interstellar classification criteria more explicitly and to describe what is rare in that classification in a way that remains anchored to measurement rather than to impression. Classification as interstellar is not a matter of appearance or of mood in the data. It is a matter of whether the orbit as measured is bound to the Sun or not. In this region, the focus stays with the criteria used to make that decision, with the careful role of reference frames, and with the specific ways uncertainty can influence early conclusions. If 3I Atlas is doing something astronomers rarely see, one clear sense of rarity is that an object can be measured as unbound with confidence and tracked long enough to study, because such cases are uncommon in the current observational record. The most direct criterion is orbital energy. In the idealized two-body case of an object moving only under the Sun's gravity, the sign of the specific orbital energy determines whether the orbit is bound. Negative energy corresponds to an ellipse. Zero energy corresponds to a parabola. Positive energy corresponds to a hyperbola. In practice, orbit solutions are expressed with orbital elements, and eccentricity is a convenient proxy. Eccentricity less than 1 indicates an ellipse equal to 1, a parabola greater than 1, a hyperbola. But eccentricity is not a complete description. It is a parameter estimated from data with an uncertainty. A best fit eccentricity slightly above 1 does not automatically prove interstellar origin. The question is whether the orbit remains hyperbolic after accounting for planetary perturbations and after expressing it in a barycentric frame that better represents the solar system's overall motion. The barycentric frame matters because the Sun is not fixed at the center of the solar system's mass. The giant planets, especially Jupiter, shift the barycenter away from the Sun. An orbit expressed relative to the Sun can show apparent hyperbolicity that reflects the Sun's motion about the barycenter, particularly when data arcs are short or when observations cluster in time. The barycentric frame reduces this effect and yields a more stable assessment of inbound and outbound energy at large distance. Therefore, a robust interstellar classification relies on barycentric orbital elements and on the asymptotic speed in that frame. Asymptotic speed, sometimes described as velocity at infinity, is the speed the object would have relative to the Sun when far away after removing the acceleration due to solar gravity. It is derived from the orbit's energy. For a bound object, this speed is zero by definition because it does not escape. For an unbound object, it is a positive value. If the value is small, the orbit is close to parabolic and classification becomes sensitive. If the value is large, the orbit is strongly hyperbolic and classification is robust. In marginal cases, uncertainty in the orbit can shift the derived asymptotic speed across zero. Therefore, the question becomes statistical. Does the distribution of possible orbits consistent with the data remain unbound, or does it include bound solutions? The answer depends on the covariance of the orbit fit and on the quality and span of the data. Planetary perturbations are another key part of classification. A solar system object can be scattered by a giant planet and placed onto a hyperbolic heliocentric trajectory, at least temporarily. Such an object is not interstellar. It is a solar system body that gained energy through gravitational interaction. To distinguish this case from an interstellar arrival, astronomers examine the inbound barycentric orbit before any close planetary encounter. If the object is already unbound on the way in, it is a true interstellar visitor. If it is bound on the way in but becomes unbound on the way out due to a planetary encounter, it is not interstellar in origin, even though its heliocentric trajectory after encounter is hyperbolic. Therefore, timing and geometry of encounters matter. The orbit solution must include planetary positions accurately, and the data arc must be sufficient to constrain the inbound path. Non-gravitational forces complicate classification in subtle ways. If the object is active and experiences recoil from outgassing, that recoil can slightly alter the trajectory. Over time, a small acceleration can change the best fit eccentricity and the inferred energy. For most comets, the effect is not large enough to turn a clearly bound orbit into a clearly unbound one. But for marginal cases near the boundary, it can shift parameters enough to matter. Therefore, if residuals suggest non-gravitational acceleration orbit solutions may be computed both with and without non-gravitational terms to test robustness. If the classification depends strongly on whether such terms are included, then confidence in the interstellar designation is lower until the physical cause of the acceleration is better constrained. Measurement systematics can also mimic hyperbolicity. If early astrometric points have a bias, the orbit fit can be skewed. For faint objects, the centroid can shift due to background blending or coma asymmetry. Timing errors can shift the predicted position along the track. Catalog errors can introduce consistent offsets. Therefore, interstellar classification requires not only more data, but more diverse data measurements from different observatories, instruments, and reduction pipelines. Diversity helps reveal and cancel systematic biases. If the hyperbolic nature persists across diverse datasets and over a long arc, confidence grows. In practical terms, the process is conservative. Orbit fits are updated as new observations come in. The statistical confidence in eccentricity above 1 is tracked. The asymptotic speed and inbound direction are refined. If the solution converges toward a stable hyperbolic orbit with uncertainties small enough that a bound solution is extremely unlikely, the object is treated as interstellar in a robust sense. The label is then a summary of a mathematical conclusion, not a claim about the object's composition or behavior. If 3I Atlas is doing something rarely seen, the rarity can be framed cleanly as a rarity in measured category, combined with a rarity in observational opportunity. An interstellar object that is detected early enough and tracked long enough yields a richer dataset than the few cases known. It allows more precise measurement of non-gravitational effects if present. It allows repeated photometry and spectroscopy across changing geometry. It allows comparisons that are otherwise limited by short arcs and faintness. The rarity is therefore not only that the object exists, but that it is observed well. The limitations remain. Even with a robust interstellar classification, the origin system is generally unknown. The inbound direction can be traced to a region of the sky, but over the timescales of travel between stars, small uncertainties grow, and stellar motions complicate backtracking. The galaxy's gravitational field and close stellar encounters can alter trajectories. Therefore, identification of a parent star is typically not possible with high confidence. This does not weaken the interstellar classification. It simply defines what that classification does and does not provide. In this region, the disciplined description ends with a clear boundary. Interstellar means unbound, inbound, barycentric motion established by orbit fits that remain robust under uncertainty and under checks for systematics and non-gravitational effects. It does not mean unusual chemistry. It does not mean engineered behavior. It does not mean a known origin. It is a statement about trajectory. The next inward steps can then describe the forces acting on the object and the way light reveals its state using this classification as a stable outer label rather than as an interpretive leap. With classification held as a trajectory statement, the next layer inward is the field of forces acting on 3I Atlas as it moves through the solar system. At the largest scale, gravity dominates, but the environment includes additional influences that can become measurable when objects are small, active, or observed with high precision. In this region, the focus stays with the external forces and perturbations, solar gravity, planetary gravity, sunlight, as both heating and pressure, and the solar wind as a shaping influence on any charged outflow. The goal is to describe what forces are available and how they are expected to appear in measurements before moving inward to the object's own light and physical response. Solar gravity sets the main path. It accelerates the object inward and later decelerates it outward. In orbit computations, the Sun is not treated as a simple point in isolation, but as the primary mass in a system that includes the planets. At large distances, the Sun's pull is weaker, but it still defines the curve of the trajectory. The object's speed increases as it falls inward, and the rate of this increase is predictable. This predictability is why residuals are meaningful when gravity is modeled well. Any persistent mismatch between observed and predicted positions points to either measurement systematics or an additional force. Planetary gravity acts as a set of time-dependent perturbations. Each planet pulls on the object, but the effect depends on distance and alignment. Jupiter is the strongest perturber because of its mass. Saturn can matter as well. The smaller planets contribute less, but in high-precision orbit work they are still included. The perturbations can change the object's orbital elements over time, bending the path and altering future predictions. If the object passes relatively near a giant planet, the encounter becomes a sensitive region where small uncertainties in the inbound track can produce larger differences in the outbound track. This sensitivity can make the orbit appear to shift as new observations are added. The shift is not the object changing course. It is the predicted path becoming more precise as the initial conditions are refined. Sunlight introduces two environmental influences. The first is heating. Heating drives activity, and activity can drive non-gravitational acceleration. Heating is also spatially uneven because it depends on illumination geometry and rotation. But at this stage, heating is treated as an external input. Sunlight delivers energy, and the object's response will be described later. The second influence is radiation pressure. Radiation pressure is the momentum transfer from photons. For a solid nucleus of typical size, the effect is usually too small to matter in orbit determination over short times. For dust grains, it matters greatly and shapes tails. For an extremely small nucleus or for fragments, radiation pressure can become measurable. The effect acts mostly away from the Sun. Its magnitude depends on the object's area-to-mass ratio and on how efficiently it absorbs and reflects light. In practice, when an orbit fit suggests a small radial acceleration away from the Sun radiation, pressure is one candidate mechanism, but it must be consistent with independent constraints on size and mass. The solar wind is a third environmental influence. It is a plasma flow carrying magnetic fields. It does not significantly alter the nucleus trajectory because the nucleus is neutral and massive relative to the forces involved. But the solar wind shapes ionized gas in the coma if activity exists. When molecules in a coma are ionized by sunlight, they become tied to the solar wind's electric and magnetic fields and can be swept into an ion tail. Ion tails can respond rapidly to changes in solar wind conditions. This can create fine structure and variability in coma morphology. For a faint, distant object, such features may not be detectable, but the mechanism remains part of the physical environment. The external force field also includes subtler influences that are usually secondary, but worth naming because they can enter high-precision discussions. One is relativistic correction near the Sun, a small effect on motion that becomes relevant for very precise orbit fits. Another is the gravitational influence of large asteroids, which is usually negligible for a passing object compared with planets, but can be included if required. These influences rarely dominate the narrative, but belong to the complete accounting of forces in precise orbit modeling. Doing something astronomers rarely see in this external forces region can mean that the object's motion is measured with sufficient precision that small non-gravitational effects become detectable at larger distances than usual. It can also mean that the object's trajectory passes through a geometry where planetary perturbations are unusually informative, allowing a strong test of the orbit model. Or it can mean that the object's activity, if present, begins far enough out that outgassing-driven forces become relevant earlier than expected for typical water-driven comets. None of these require an unusual force. They require a particular combination of object properties, solar distance, and observational coverage. The environment also includes the observational environment, which interacts with force interpretation. A faint object is measured with larger uncertainty. Larger uncertainty can hide small forces, or can create apparent forces through bias. If a coma is present and asymmetric, the center of light can shift, producing astrometric residuals that look like acceleration. If the object trails in images due to rapid angular motion, centroid measurement can be biased. If background stars contaminate, both brightness and position can be shifted. Therefore, in force interpretation, measurement context is treated as a parallel layer. Before an additional physical force is invoked, the possibility of systematic measurement bias must be evaluated. At this stage, the practical method is to compare orbit fits under different assumptions. A gravity-only model is the baseline. If residuals are consistent with expected measurement errors, no additional forces are required. If residuals show a persistent pattern, alternative explanations are tested. Are certain observatories producing biased positions? Does the residual pattern correlate with seeing or with image trailing? Does the pattern correlate with times when the object passes through dense star fields? If measurement factors do not explain the pattern, then additional forces are considered. Non-gravitational acceleration due to outgassing is the most common. Radiation pressure is considered when the object's size and mass constraints allow a significant area-to-mass ratio. Planetary perturbations must also be treated carefully in this context. If the object is approaching a region where Jupiter's influence is strong, small differences in the predicted track can appear quickly. An orbit fit can appear unstable simply because the solution is sensitive near that region. In this case, the rare aspect may be the combination of an interstellar-like path and a planetary encounter that allows an unusually clear measurement of gravitational deflection. Such an encounter can be a valuable test if the object's trajectory matches gravitational predictions through the encounter. Confidence in orbit modeling is strengthened. If deviations persist beyond what gravity predicts, then non-gravitational forces become more plausible. The external force field therefore sets the stage for later interpretation without deciding it. Gravity provides the skeleton of motion. Planets add joints that can bend the path. Sunlight provides energy and a small push. The solar wind shapes ionized outflow if it exists. Measurement context determines which effects can be seen. In this region, the object is not yet described as a specific surface or chemistry. It is described as a body moving through a well-defined physical environment, whose influences can be listed, modeled, and tested. The rarity, if present, is a rarity of detectability and of measurable subtlety, a case where the external force accounting may need to include small terms earlier or more clearly than is typical. Light is the most continuous evidence available for 3-eye atlas, and in many cases it is the only evidence that can be gathered night after night as the object moves through changing geometry. In this region, the focus stays with light as a broad indicator of state. The aim is not to assign a precise size or composition yet. It is to describe what brightness, its change over time and its variability can reveal in a disciplined way, and why some patterns are rare in the observed record even when they arise from ordinary physics. The starting point is apparent brightness, the amount of light received by a telescope. Apparent brightness changes for simple geometric reasons. If the object is farther from Earth, less light reaches the telescope. If it is farther from the Sun, less sunlight reaches the object to be reflected or scattered. These geometric effects can be corrected to some extent by converting apparent brightness into a standardized value such as an absolute magnitude. Absolute magnitude is the brightness the object would have at a standard distance from both the Sun and Earth under a reference geometry. But this correction depends on a phase function, a model for how brightness changes with phase angle, the Sun object-observer angle. Different surfaces and different dust environments have different phase functions. Therefore, corrected brightness still carries model dependence. Even so, these corrections help distinguish changes driven mainly by distance from changes driven by intrinsic evolution. Intrinsic evolution in brightness can come from rotation. A rotating body presents different cross-sections to the observer over time. If the body is elongated, the cross-section varies and brightness rises and falls. If the surface reflectivity varies, brightness can also change even if the shape is nearly spherical. These variations form a light curve. In the simplest case, the light curve repeats with a stable period, and that period is the rotation period, or half of it, depending on the symmetry of the light curve. In a more complex case, the light curve can contain multiple periods or changing amplitudes reflecting tumbling rotation, evolving activity, or changing viewing geometry. Brightness can also change because of dust and gas around the object. If the object is active, it can develop a coma. A coma adds scattering area. The nucleus may contribute only a fraction of the light. In that case, brightness is no longer a direct proxy for the nucleus. It becomes a proxy for the combined system of nucleus and surrounding material. Activity often increases as the object approaches the Sun, but the rate and onset depend on volatile content and surface properties. Therefore, a brightness evolution that deviates from typical comet trends can reflect differences in activity, differences in dust properties, or differences in geometry. Geometry can produce rare-looking effects through scattering. Dust grains can scatter light strongly in certain directions. Forward scattering, where dust scatters sunlight preferentially in the direction the light is traveling, can make a dust-rich coma appear much brighter at certain phase angles. This can create a brightness surge that is not due to increased activity, but due to viewing angle. In a dataset, such a surge can look unusual because it can be large and can occur over a limited time window. It becomes rarer in the observed record because it requires both a dusty coma and a geometry that produces high forward scattering enhancement while the object is still observable. Not every object passes through such a geometry during an accessible observing period. The measurement of brightness must also contend with the observational environment. Sky background brightness changes with moonlight and atmospheric conditions. Seeing the atmospheric blurring of images changes the apparent size of point sources and can affect how much light falls into a fixed photometric aperture. If seeing worsens, a fixed aperture captures a different fraction of the object's light. This can mimic variability. Therefore, careful photometry uses aperture corrections or uses differential measurements relative to field stars. Calibration differences between observatories can also introduce offsets. These must be corrected if light curves from multiple sources are combined. For a faint moving object, background contamination is a persistent challenge. If the object passes near a star or faint galaxy, their light can blend, making the object appear brighter and shifting the measured centroid. As the object moves, the blend changes, producing apparent variability not tied to the object. Surveys reduce this with image subtraction and careful background modeling, but at faint levels, errors remain. Therefore, when a brightness change is reported, it is checked against the object's sky path to see whether it coincides with a crowded field or with a close pass to a background source. Within these constraints, a set of observable patterns becomes meaningful. A steady brightening that follows a smooth trend with distance suggests either a bare nucleus or a stable low-level activity with constant dust properties. A brightening that accelerates faster than distance trends suggests increasing activity or strong phase angle effects. A sudden jump can suggest an outburst, a rapid release of dust and gas from a surface rupture or pressure release. A periodic modulation suggests rotation and possibly a stable nucleus-dominated component. An irregular modulation suggests tumbling or variable activity. The key is that these patterns are interpreted as constraints, not as unique diagnoses. Doing something astronomers rarely see in the light as evidence region can mean that the object's brightness evolution sits outside the most familiar envelopes for known populations. A candidate interstellar object might show a brightness evolution that differs from typical solar system comets, either because its volatile inventory differs or because its surface is less processed by repeated solar heating, or because its dust grain properties differ. It might also show a light curve that remains clean and stable despite faintness, allowing a rotation period to be measured unusually early. Conversely, it might show brightness behavior that resists clean modeling with changes that cannot be explained by distance alone, and that require careful accounting of phase dust, scattering, and potential episodic activity. Each of these outcomes can be rare in the observed record because they require high-quality time series data on a faint object, which is itself uncommon. The most disciplined approach is to separate what the light directly provides from what it implies. Directly light provides brightness in a filter at a time and changes in that brightness. It provides color indices when multiple filters are used. It provides a light curve when sampling is dense enough. It provides hints of extension when the object's profile differs from stars. Indirectly, it implies rotation activity and dust properties, but only through models. A calm description holds these as layered inferences. If 3I Atlas shows light behavior that appears rare, One responsible explanation can be that the object is being observed under an unusually complete cadence for its faintness, allowing subtle variations to be measured. Another can be that its dust-scattering properties produce a pronounced phase-dependent brightening. Another can be that its activity begins at larger distances than commonly observed, producing a detectable coma earlier. All of these remain within known physics. The rarity lies in the intersection of object properties and observational opportunity. By the end of this section, light has been placed as a broad diagnostic. It is a continuous record shaped by distance geometry rotation and activity filtered through measurement conditions. It can contain rare-looking patterns without requiring rare physics. It prepares the next inward step, where colors and spectra offer broader clues about what is scattering the light and what gases, if any, are present. After brightness as a broad signal, the next inward layer is how that light is distributed by wavelength. This layer is reached through colors measured in different filters and through spectra that disperse light into a continuous record. For 3I atlas wavelength information is often harder to obtain than positions and basic photometry because it requires more telescope time and higher signal. Yet even sparse wavelength data can tighten interpretation. In this region, the focus stays with what colors and spectra can suggest about the scattering material and about the presence or absence of gas, while keeping each conclusion bounded by detection limits and by instrumental constraints. Colors in astronomy are differences in brightness between filters. They are a way to describe whether an object reflects more light at longer wavelengths or at shorter wavelengths. A surface or dust environment that reflects more strongly at longer wavelengths is described as redder. One that reflects more evenly is described as more neutral. These terms do not refer to the object's visual appearance to the eye. They refer to measured slopes and reflectance relative to sunlight. For small bodies, a red slope can be associated with complex organic residues and long-term radiation processing, but it can also be produced by dust grain scattering properties. Dust grains, especially if they are small or porous aggregates, can have wavelength-dependent scattering that produces a red slope, even if the underlying composition is not unusual. Therefore, color is a constraint on scattering behavior, not a direct chemical fingerprint. A spectrum offers more detail. A reflected light spectrum often shows a continuum, a smooth curve, that is the solar spectrum modified by the object's reflectance. If the object is inactive and there is no coma, the continuum reflects the surface. If a coma is present, the continuum can reflect dust. In many comet observations, the dust continuum dominates the optical spectrum, and the nucleus surface is not directly visible. This makes it difficult to separate nucleus composition from coma dust properties. Still, the continuum slope can be compared to known classes of objects. Some outer solar system bodies show very red slopes. Some asteroids show more neutral slopes. Comet dust often shows modest reddening. The overlap is broad. A spectrum can indicate whether the object sits within the typical range or toward an extreme, but it rarely provides a unique label by slope alone. Emission features in a spectrum indicate gas. Gas emits light at specific wavelengths when molecules are excited by sunlight and then re-emit. This process is often fluorescence. In cometary coma, many detected emission features come from fragments and radicals produced when sunlight breaks parent molecules. The measured species therefore trace photochemistry as well as original composition. For example, water may not be directly visible in optical spectra, but its photodissociation products can be. Carbon-bearing species can appear in particular bands. In the infrared, vibrational bands can reveal parent molecules more directly, but infrared observations are harder from the ground due to atmospheric absorption and thermal background. A key constraint for 3I Atlas is that faint objects yield low signal-to-noise spectra. Signal-to-noise ratio determines whether a weak emission line can be distinguished from noise and from imperfect sky subtraction. The night sky itself has emission lines, especially in the near-infrared, and it can leave residuals after subtraction. Calibration requires observing standard stars to correct for the instrument response and for atmospheric transmission. Small calibration errors can create artificial slopes or spurious features. Therefore, the absence of detected gas lines may reflect insufficient sensitivity rather than true inactivity. Conversely, a claimed faint feature must be checked for consistency across multiple exposures and nights. Multi-band photometry can supplement spectroscopy. If colors are measured in several filters, they can reveal whether the object has a steep spectral slope, whether it is unusually red, or whether it has an excess in a filter that includes a known emission band. However, broad filters mix continuum and lines. A weak emission line may not produce a large color change. Narrowband filters designed for comet gas species can isolate emissions, but such observations are specialized and not always available. Therefore, color-based gas inferences are cautious unless supported by spectra. Thermal infrared adds another important wavelength window. In thermal infrared, the object emits heat rather than reflecting sunlight. Thermal emission depends on size, surface temperature, emissivity, and thermal inertia. Emissivity is the efficiency with which a surface emits thermal radiation. Thermal inertia describes how quickly a surface heats and cools. If thermal measurements are available, they can help separate size and albedo. A bright object in reflected light could be large and dark, or small and reflective. Thermal emission helps distinguish these cases because a larger object emits more heat. But thermal measurements for distant faint objects are challenging. They often require space-based telescopes and long integration times. If a thermal detection is not possible, an upper limit can still constrain size. An object larger than a certain size would likely have been detected thermally at a given distance under reasonable assumptions. Radio observations can search for specific molecules through their rotational transitions. Carbon monoxide, for example, has radio lines that can be targeted. Radio detection can provide a direct estimate of production rate. Yet radio observations require precise ephemerides and often require the object to be bright enough in gas emission. For a faint interstellar candidate, radio non-detections are common. Non-detections are still useful because they provide upper limits and can rule out very high production rates of certain species. Doing something astronomers rarely see in this wavelength region can mean that the object shows a combination of continuum and line behavior that is uncommon. It might show a strong dust continuum with little gas emission detectable, suggesting dust-rich activity. It might show gas signatures at larger distances than usual, pointing to supervolatile-driven activity. It might show a reflectance slope that sits at an extreme compared with typical comet dust, suggesting unusual grain properties or surface processing history. It might also show an almost featureless continuum, despite other hints of activity, which would be rare mainly because observers often expect at least some detectable gas when activity is present. Yet such a mismatch can occur naturally if gas production is low or if the dominant gases are difficult to detect in available wavelength windows. In all these cases, the discipline statement returns to thresholds. What was the sensitivity of the observation? Which wavelength region was covered? Which filters were used? What were the sky conditions? Were there repeated observations? Did different instruments agree? The strongest claims are those supported by repeatable features and by consistent calibration. The weakest claims are those that hinge on single-night low signal-to-noise features. Color and spectrum also connect back to the light curve discussion. If brightness variations are observed, it matters whether colors change with brightness. If the object becomes redder when brighter, that could suggest increased dust contribution. If colors remain constant while brightness changes, that could suggest shape-driven rotation or uniform dust properties. If an emission band strengthens while continuum stays similar, that could suggest changing gas production. These comparative patterns can be measured even when absolute calibration is difficult, because relative changes are often more robust. Yet they still depend on consistent observing setups. By the end of this section, 3I Atlas is framed by what wavelength data can and cannot deliver at this stage. It can indicate whether the light is dominated by dust or surface reflection. It can detect gas if emission lines are strong enough. It can place upper limits when lines are absent. It can narrow size and albedo if thermal data exist. It can suggest but not prove differences in composition relative to typical solar system comets. This prepares the next inward step, where the immediate envelope of activity, the coma and its onset, is described as the physical mediator between external sunlight and measured light and motion. From colors and spectra, the next inward region is the immediate space around 3I Atlas, where any released material forms a coma. The coma is the interface between the object's surface and the wider solar system environment. It is also the region where many rare-looking behaviors first become visible, because a small change in gas flow or dust release can produce a detectable change in brightness or morphology. In this section, the focus stays with coma onset weak activity and the observational techniques used to detect them while holding every inference within the limits of what can be measured. A coma forms when material leaves the surface. The primary driver is heating from sunlight. If volatile material is present near the surface, it can sublimate, turning directly from solid to gas. The escaping gas expands into space and can carry dust grains with it. The resulting cloud can scatter sunlight and make the object appear brighter and more extended than a bare nucleus. The structure of the coma depends on how much gas is produced, how dust is lifted, and how the outflow is shaped by rotation and by external forces like radiation pressure and the solar wind. At large distances, coma onset is often subtle. Sunlight is weak and water-ice sublimation is minimal. If activity is present far out, it is more likely to be driven by more volatile substances, such as carbon monoxide or carbon dioxide, or by the release of trapped gases from amorphous ice crystallization. These are standard cometary mechanisms, considered for distant activity. Yet whether they operate depends on the object's near-surface composition and structure. An interstellar visitor might carry preserved volatiles near the surface if it has been cold for a long time, but it might also carry a processed crust that insulates the interior. Therefore, the onset distance is not fixed. It is an outcome of material properties and thermal history. Observers detect a coma by comparing the object's appearance to that of nearby stars. In a typical ground-based image, stars have a point spread function set by the atmosphere and the telescope. A bare nucleus should have a similar profile. A coma adds a faint extended component, making the profile broader or making the wings brighter. This can be measured by comparing the full width at half maximum or by measuring how brightness increases with aperture size. If the object's brightness increases more than star's brightness as the aperture grows, it suggests extended emission. But seeing changes, tracking errors, and trailing can mimic extension. Therefore, confidence usually comes from repeated detections of extension under different conditions and ideally from multiple observatories. A coma can also be inferred from the way brightness behaves relative to expectations. If brightness rises faster than would be expected from distance changes alone, and if phase effects are not sufficient to explain it, activity becomes more plausible. But brightness is influenced by dust scattering properties and by phase angle, especially if forward scattering is strong. Therefore, brightness trends alone are not definitive. They are a prompt for deeper imaging and for profile analysis. Morphology, when detectable, provides additional clues. A symmetric coma suggests relatively uniform outflow across the sunlit hemisphere or many distributed active patches. An asymmetric coma suggests localized jets. Jets can form when sunlight reaches a patch of exposed ice or when gas escapes through a preferred crack. As the object rotates, jets can sweep and produce fan-like structures. These structures can be faint and require high signal-to-noise imaging, often with stacking of multiple exposures aligned on the moving object. Stacking increases sensitivity by averaging down noise, but it can blur time-variable structures. Therefore, observers choose stacking strategies depending on the question. Detect any coma or resolve morphology. Dust tails, if present, are shaped mainly by radiation pressure. Once dust grains are released, sunlight pushes them away from the sun. Smaller grains accelerate more strongly. Larger grains lag. Over time, dust released at different moments forms a tail that can curve along the orbit. The tail direction is not always directly away from the sun, because the grains carry the nucleus's orbital velocity when released, and because radiation pressure modifies their subsequent motion. An ion tail, in contrast, is shaped by the solar wind and tends to align more closely with the anti-solar direction. For a faint distant object, ion tails are often too faint to detect, and dust diagnostics dominate. Doing something astronomers rarely see in this coma region can mean that the object shows measurable coma signatures at a distance where many known comets remain quiescent. That would suggest a volatile inventory or thermal process that allows early gas release. It can also mean that coma signatures are unusually weak, while other indicators, such as orbit residuals, suggest non-gravitational acceleration. In such a case, the object might be releasing gas without much dust, producing thrust, with little visible coma. Alternatively, the orbit residuals might be influenced by centroid bias from a faint asymmetric coma, producing an apparent acceleration that is partly observational. Both possibilities are natural, and both require careful separation. Quantifying activity from coma brightness is difficult because it depends on dust properties. Observers can use comparative parameters that scale with dust scattering cross-section in a defined aperture. These parameters are useful for comparing relative dustiness across objects and times, but they are not direct mass loss rates without assumptions about grain size, distribution, density, and velocity. Gas production rates, if emission lines are detected, can be estimated more directly, but they still depend on models of excitation and on photodissociation lifetimes. Therefore, the correct approach is to treat early activity estimates as ranges and to emphasize upper limits when detections are not secure. The observing environment continues to matter strongly here. Moonlight raises sky background and reduces sensitivity to faint coma. Poor seeing spreads light and can hide a low surface brightness coma within the point spread function. The object's motion can cause trailing that complicates profile comparisons. Crowded star fields can contaminate. Therefore, a sequence of consistent detections is more important than a single deep image. When observers report coma detection, they often accompany it with comparisons to field stars and with descriptions of seeing conditions. If a coma is present, it affects astrometry. The measured centroid can shift if the coma is asymmetric. This can create systematic offsets in positions that vary with viewing geometry and with the direction of the tail. If such shifts are not accounted for, orbit fits can show residual patterns that might be interpreted as non-gravitational acceleration. Therefore, orbit analysts and observers often coordinate. They examine whether astrometric residuals correlate with coma appearance. They compare data from telescopes with different resolutions. They test whether restricting astrometry to high-quality near-stellar images changes the inferred acceleration. This interplay between coma physics and orbit fitting is a standard part of comet work and becomes particularly important for objects of special interest. By the end of this section, 3I Atlas is described as potentially surrounded by a faint measurable envelope whose onset and evolution reflect near-surface physics under sunlight. The coma, if present, is a mediator. It converts heat into escaping material, converts escaping material into scattered light, and can convert asymmetric flow into subtle thrust. The rarity, if present, lies in how early, how weak, or how decoupled this coma behavior is compared with typical observed cases. The next inward step examines the dynamical side of the same story, how deviations from gravity-only motion are inferred, and what they require in terms of physical forces and observational caution. From the coma as a physical envelope, the narrative moves inward to the dynamical signature that can emerge from that envelope non-gravitational deviations in the trajectory. These deviations are not directly observed as forces. They are inferred from small, persistent mismatches between predicted and measured positions. In this region, the focus stays with how such deviations are detected, how they are modeled, and how ordinary mechanisms can produce them. If 3I Atlas is doing something astronomers rarely see, the rarity can be framed as the detection of subtle accelerations at large distance, the difficulty of fitting a stable model, or a mismatch between visible coma and inferred thrust. Orbit determination begins with a gravitational model that includes the Sun and the planets. This model predicts positions at observation times. Astrometric measurements provide actual positions. The differences are residuals. In a well-behaved case, residuals are small and randomly distributed, consistent with measurement uncertainties. In a case where an additional influence exists, residuals can show structure. The object may consistently appear ahead of the predicted position along its path, or consistently offset in a particular direction. When such patterns persist across many nights and observatories, the simplest interpretation is that the model is missing a term. Non-gravitational terms are introduced as small accelerations, with components in defined directions, radial transverse and normal. Radial is away from or toward the Sun. Transverse is along the direction of motion. Normal is perpendicular to the orbital plane. These components can be fitted as parameters. The fit seeks values that minimize residuals. A successful fit reduces systematic residual patterns and leaves residuals that look random. The fitted parameters are then treated as measured quantities with uncertainties. Yet these parameters are not purely physical constants. They are model-dependent. The functional form of how acceleration varies with distance from the Sun matters. For comet-like outgassing, acceleration is often modeled with a distance scaling function tied to sublimation. In the inner solar system, water-ice sublimation dominates many comets, and empirical functions exist that approximate how water sublimation depends on solar distance. But for distant activity, water-based functions can be inappropriate. Carbon monoxide and carbon dioxide can sublimate at larger distances with a different distance dependence. If 3I Atlas is active at large distance, a water-based model can misrepresent the acceleration's shape and produce a fit that is unstable or that changes as the object moves. In such cases, the fitted non-gravitational parameters may shift over time, not because the object's physics changes dramatically, but because the chosen model does not match the true dependence well. Analysts may test alternative scaling functions or allow more flexible forms to see whether the residuals support a different pattern. Outgassing itself can produce accelerations in directions beyond purely radial. If gas escapes uniformly from the sunlit hemisphere, the net recoil tends to point away from the Sun. If gas escapes from localized vents, the net recoil direction can depend on the vent location and on rotation. Over many rotations, the net effect can average to a direction that depends on the spin axis orientation and on the distribution of active areas. If the spin axis is tilted, the thrust direction can include components out of the orbital plane. Therefore, a measured normal component is not inherently unusual. It can arise from ordinary asymmetric outgassing. However, before physical causes are emphasized, measurement systematics must be considered. A faint coma can bias the astrometric centroid. If the coma is asymmetric, the center of light shifts in the tailward direction. The tail direction depends on solar geometry and dust dynamics. This shift can mimic an acceleration because it creates a systematic offset in measured positions. The offset can vary with phase angle and with viewing geometry, producing patterns in residuals that change with time. If the object is faint, the centroid is already uncertain, and the presence of a faint coma can introduce biases comparable to the effect being measured. Therefore, analysts test whether the inferred acceleration persists when using only the most precise astrometry, or when using data from telescopes that can better resolve the nucleus region, or when applying coma-aware centroiding methods. Trailing is another systematic factor. If the object moves quickly across the sky, it can trail during exposures. A trailed source has a centroid that can depend on the fitting method. Some pipelines fit a point source and bias the centroid. Others fit a trailed profile and reduce bias. Differences between pipelines can create systematic residual patterns. Therefore, a careful non-gravitational analysis compares data sets and checks whether residuals correlate with exposure time and angular speed. Radiation pressure is an alternative mechanism for small accelerations, especially in the radial direction. Radiation pressure is proportional to area and inversely proportional to mass. For a typical nucleus, it is too small to matter. For a very small object or for fragments, it can be measurable. A purely radial acceleration that scales with the inverse square of solar distance can be consistent with radiation pressure. Outgassing can also produce a radial acceleration, but its distance dependence can differ, and its direction can vary. Distinguishing radiation pressure from outgassing requires combining dynamical data with size and brightness constraints. If the object's estimated size is large, radiation pressure becomes less plausible as a dominant driver. If the estimated size is small, it becomes more plausible. Yet size estimates are uncertain, especially if a coma contributes to brightness. Therefore, the distinction can remain uncertain without additional constraints, such as thermal measurements or direct gas detections. Doing something astronomers rarely see in this region can mean that the object shows a measurable acceleration at a distance where most comets have negligible non-gravitational effects in the available data. This could reflect an early onset of supervolatile-driven activity. It could reflect a small mass that makes modest thrust produce measurable acceleration. It could also reflect unusually precise astrometric tracking for a faint object, allowing small effects to be detected. Alternatively, it can mean that the acceleration is difficult to fit with standard functions, suggesting time-variable or geometry-dependent outgassing. Time variability can arise from rotating jets, episodic venting, or changes in activity as new surface areas are illuminated. Such behavior is not exotic, but it complicates modeling and can appear rare because many objects are not observed well enough for the complexity to be evident. The correct handling of these deviations is to treat them as constraints rather than as conclusions. A fitted acceleration implies that the simplest gravity-only model is insufficient for the dataset. It implies that either a real physical force is acting or a systematic measurement bias exists. The next step is to test robustness, remove suspect data change, weighting test different coma treatments, and see whether the acceleration remains. If it remains, then physical mechanisms are considered and bounded. If it vanishes, then measurement biases are the likely explanation. This region ends with a calm statement. Non-gravitational deviations are a measurable possibility for 3I Atlas inferred through residual patterns and model fitting. They can be produced by ordinary outgassing recoil by radiation pressure in special size regimes, and they can be mimicked by coma-induced centroid shifts and by trailing biases. The rarity if present lies in how clearly these deviations are measurable how early they appear, or how they resist standard modeling. The next inward step moves from dynamics to the body itself, where size and shape bounds are considered as a way to connect light and acceleration to physical scale. With deviations from gravity held as a measured constraint, the next inward region is the physical scale of 3I Atlas as a whole, how large it is, how it might be shaped, and how those properties are bounded by the evidence already described. In this region, the focus stays with size and shape as inferred quantities, not as directly observed facts. The object is still unresolved in most observations, meaning telescopes see a point of light rather than a disk. Therefore, size and shape must be inferred from brightness, from color and spectral context, and from rotational variability. The aim is to describe these inferences calmly, to track their assumptions, and to show why apparently shifting estimates can occur without any change in the object itself. A brightness measurement by itself does not uniquely determine size. Reflected light depends on the cross-sectional area presented to the sun and to the observer, and it depends on albedo, the fraction of sunlight reflected. A large, dark body can reflect the same amount of light as a smaller, brighter body. Because albedo is often unknown for newly discovered objects, astronomers adopt plausible ranges based on similar populations. For comet nuclei and many dark asteroids, low albedos are typical. For some icy bodies, higher albedos occur. Using a low assumed albedo yields a larger inferred size. Using a higher assumed albedo yields a smaller inferred size. The result is therefore a size range rather than a single number. The width of that range reflects how uncertain albedo is. Activity can widen the uncertainty further. If 3I Atlas is surrounded by dust, the dust can dominate the brightness. Dust increases the effective scattering area without increasing the nucleus size. In such a case, brightness-based size estimates can be too large if the coma contribution is not accounted for. The problem is that coma contribution can be subtle. A weak coma may not be obviously resolved, yet it can still add significant scattered light. Therefore, a cautious size estimate considers whether the object's profile differs from stars, whether brightness depends strongly on aperture size, and whether colors suggest dust scattering. If evidence suggests coma, the brightness is treated as an upper bound on nucleus size rather than a direct measure. Thermal infrared observations, if available, can reduce this ambiguity. In thermal infrared, the object emits heat. Thermal emission depends more directly on size because larger objects emit more total energy. Combining thermal emission with reflected light can constrain both size and albedo. However, thermal measurements of faint distant objects are difficult and often unavailable. If only an upper limit exists, it still provides a size constraint. An object larger than a certain size would likely emit enough heat to be detected. Such constraints depend on assumed emissivity and temperature distribution, but they are often less sensitive to albedo than reflected light estimates. Shape inference begins with light curve amplitude. If brightness varies periodically, it suggests rotation. The amplitude of variation, how much the brightness rises and falls, can constrain elongation. An elongated body presents a larger cross-section when viewed broadside, and a smaller one when viewed end-on. This produces a double-peaked light curve, often with 2 maxima and 2 minima per rotation. For a given viewing geometry, a larger amplitude implies a more elongated shape if albedo is roughly uniform. but albedo variations can also produce amplitude. In addition, viewing geometry matters. If the rotation axis is pointed near the line of sight, the observed cross-section may change little, and amplitude may be small even if the body is elongated. Therefore, amplitude provides a lower bound on elongation rather than a precise shape. A coma can mask shape signals. If a coma adds a steady background of light, the relative variation from the nucleus becomes smaller. The light curve amplitude measured in a fixed aperture can then be reduced. If the coma itself varies, it can add irregular variability. Therefore, before using amplitude to infer shape, observers compare light curves measured in different apertures. A nucleus-dominated signal tends to be stronger in smaller apertures. A coma-dominated signal tends to persist or grow in larger apertures. This is not always decisive, but it helps separate components. Apparent changes in size estimates over time can arise from changing geometry. Phase angle affects brightness. Dust scattering, especially forward scattering, can increase brightness at certain phase angles. If brightness is interpreted as size without correcting for phase, properly size estimates can appear to shrink or grow as geometry changes. A brightening due to forward scattering can be misread as an increase in nucleus size or activity. Later, when geometry changes and brightness drops, the nucleus would appear to shrink. In reality, the scattering conditions changed. Therefore, size inference must track phase angle and use appropriate phase functions, recognizing that dust and surfaces can have different phase behavior. Doing something astronomers rarely see in the size and shape region can mean that the inferred bounds place the object in an unusual part of parameter space. It might appear unusually small, yet dynamically show measurable non-gravitational effects, implying a low mass or strong activity. It might appear unusually large for an interstellar visitor, challenging expectations about detectability and population statistics. It might show a very large light curve amplitude, implying a highly elongated shape, which would be rare, but not unheard of. Or it might show an unusually low amplitude, despite suspected activity, suggesting either a near-spherical nucleus, a pole-on viewing geometry, or coma masking. The rarity, again, can be observational. Few objects have enough data quality to constrain amplitude and brightness evolution simultaneously at the faint end. Mass is not directly measured from size and light alone. Without a gravitational interaction that reveals mass remains uncertain. But mass enters indirectly through dynamical deviations. If a non-gravitational acceleration is measured and interpreted as outgassing recoil, then the acceleration provides a relationship between thrust and mass. If thrust can be estimated from gas production rate and exhaust speed, mass can be inferred. Often thrust cannot be estimated well because gas production is not well measured. Therefore, mass remains a broad unknown. Still, the combination of apparent brightness, inferred size range, and measured acceleration can provide consistency checks. A very large nucleus with a very large measured acceleration would require a very large thrust, which might be inconsistent with observed coma brightness or gas limits. A very small nucleus with a modest acceleration can be consistent with weak activity. These are not proofs. They are plausibility checks. A final global constraint comes from stability. If rotation period is measured and inferred, shape suggests elongation, then the object's structural integrity must be sufficient to withstand rotational stress. For small bodies with low density and weak cohesion, extremely rapid rotation is difficult. Therefore, if the object appears to rotate rapidly and to be elongated, it may require either higher internal strength or smaller size where cohesion matters more. These considerations remain conditional because size, shape, and period can all be uncertain. Yet they provide another layer of consistency. In this region, 3I Atlas is therefore described as a body whose size and shape are bounded by brightness and variability, and whose bounds can shift as assumptions about albedo coma contribution and geometry are refined. Rare-looking behavior can arise when these bounds sit in unusual combinations, such as strong dynamical effects with weak visible coma or extreme elongation inferred from light curves. The disciplined approach is to keep the chain of inference visible brightness and color lead to size ranges under albedo assumptions. Light curves lead to shape constraints under viewing assumptions. Activity can inflate brightness and mask rotation. Geometry can amplify dust scattering and distort naive size interpretations. This completes the move inward toward rotation and stability as the next controlling layer. From global size and shape bounds, the next inward region is rotation and stability, because rotation governs how sunlight is applied across the surface and how any outgassing forces are oriented over time. Rotation also determines whether activity appears steady or modulated, and whether dust and gas are released in persistent jets or in shifting patches. In this region, the focus stays with how rotation is inferred, how complex rotation can arise, and what rotation implies for structural stability in a small body like 3I Atlas. The rarity, if present, can be expressed as unusual clarity or unusual complexity in the rotational signature, or as a rotation state that interacts with activity in a way that is not often observed in detail. Rotation is inferred primarily from periodic brightness variations. A rotating body with an irregular shape or uneven reflectivity produces a light curve that repeats. In the simplest case, the light curve is stable in period and shape. Many small asteroids show such behavior. Comet nuclei can also show it when activity is weak and the nucleus signal dominates. For a typical elongated body, the light curve is often double-peaked because two broadside orientations per rotation produce two maxima. Distinguishing whether the measured period is the true rotation period or half of it requires careful analysis of light curve symmetry and sometimes additional data such as color changes or shape modeling. In practice, early period estimates can be uncertain because the dataset may not cover enough cycles or may have gaps. Gaps are common because ground-based observing is limited by daylight and weather. A period near 1 day can be especially difficult because sampling repeats at similar phases, creating aliasing. Aliasing is when different periods can fit the same sampled data because of regular gaps. Combining observations from observatories at different longitudes helps reduce aliasing by filling time gaps. Even then, a faint object may not be observable all night, and the usable window may be short. Therefore, rotation period determination is often a process of narrowing candidates rather than making an immediate definitive statement. Activity can complicate this. If 3I Atlas has a coma, the coma adds light. If the coma light is steady, it reduces the relative amplitude of rotational variation. If the coma varies, it can add noise or even produce its own periodicity, if an active jet rotates in and out of view. In such cases, the light curve may reflect the rotation of active regions rather than pure shape modulation. This is still rotation information, but it is mediated by surface processes. A periodic brightening could correspond to a jet that becomes more sunlit once per rotation. A periodic fading could correspond to the jet turning away. If multiple jets exist, multiple periodicities can appear. A more complex rotation state is tumbling or non-principal axis rotation. A rigid body has principal axes of inertia. In simple rotation, it spins around one of these axes steadily. Tumbling occurs when the body rotates around more than one axis in a coupled motion. This can happen after an impact or after asymmetric torques. For small bodies, impacts can impart tumbling. For active comets, outgassing torques can also change the rotation state. Tumbling produces light curves that are not strictly periodic, or that contain multiple periods. The light curve may drift in phase or change shape over time. This can be mistaken for changing activity or changing shape, but it can be the signature of complex rotation. Damping of tumbling occurs through internal friction. Over time, internal stresses convert rotational energy into heat, and the rotation settles into a principal axis spin. The damping timescale depends on size, internal structure, and rigidity. For a porous rubble-like body, damping can be slow and tumbling can persist for long periods. Therefore, if 3I Atlas shows complex variability that resists simple period-fitting tumbling, is a plausible state without requiring unusual causes. The rarity lies in whether the data are good enough to diagnose it clearly. Rotation is also influenced by torques from outgassing. When gas escapes from a specific region, it acts like a thruster. The reaction force produces a torque if it does not pass through the center of mass. This torque can change the rotation period and can shift the spin axis over time. Some comets show measurable changes in rotation period over a single perihelion passage. The effect depends on gas production and on the lever arm of the active region relative to the center. A small body with strong localized activity can experience significant torques. If 3I Atlas is small and has localized vents, its rotation could evolve measurably during observation, producing a light curve period that drifts. Such drift would be rare in the observed record, mainly because it requires dense time series on a faint object over a long enough baseline to measure the change. Rotation links directly to stability. A rotating body experiences centrifugal acceleration that increases toward the equator. If rotation is fast, centrifugal stress can overcome gravity and cohesion, leading to mass shedding or fragmentation. For rubble pile asteroids, there is an observed spin limit, where many bodies larger than a certain size do not rotate faster than a few hours, consistent with gravitational cohesion limits. Comet nuclei are often weaker and more porous, and their effective strength can be low. Therefore, very rapid rotation in a large, weak nucleus would be difficult to sustain. If a rapid period is inferred, it suggests either a small size where material cohesion matters more, or a stronger structure or an overestimation due to aliasing. Again, this is a consistency check rather than a definitive diagnosis. Rotation also governs thermal cycles. As the body spins, surface patches heat in sunlight and cool in darkness. The rate of heating and cooling depends on thermal inertia. A low thermal inertia surface heats quickly and cools quickly, producing strong day-night temperature swings. A higher thermal inertia surface changes more slowly, smoothing variations. These temperature cycles can modulate sublimation. If volatiles are near the surface, gas production can peak near local noon and fall at night. This can create periodic changes in coma brightness and in jet strength. If the rotation is slow, prolonged heating can allow deeper penetration of the thermal wave, potentially activating deeper volatiles. If the rotation is fast, heating may remain superficial, perhaps limiting deep activation unless cracks provide pathways. These are controlled physical consequences of rotation state. The spin axis orientation. The pole adds another level of structure. A tilted pole can create seasonal effects where one hemisphere receives more sunlight over part of the orbit. For an object approaching the sun, seasons can change the distribution of activity. This can shift jets over time and can change the direction of any non-gravitational acceleration components. In principle, pole orientation can be inferred from jet morphology changes and from the direction of non-gravitational acceleration if the data are rich enough. For faint objects, pole inference may remain uncertain. Still, the concept matters because it explains how the same object can show changing activity patterns without any change in composition, doing something astronomers rarely see in the rotation and stability region can thus mean several grounded things. It can mean that the rotation signal is unusually clean despite faintness, allowing a stable period determination and perhaps even shape modeling. It can mean that the rotation is complex with tumbling signatures that are rarely resolved because data are seldom dense enough. It can mean that rotation appears to be changing measurably due to outgassing torques, producing a drifting period. Or it can mean that inferred rotation is near stability limits, making the object a candidate for shedding material, which could connect to observed outbursts or fragmentation if those occur. Each of these interpretations remains within the physics of small bodies. By the end of this section, rotation is held as the governing clock of the object's response to sunlight and the mediator between activity and dynamics. It provides a pathway to explain both periodic brightness changes and time-variable non-gravitational effects. It also provides stability constraints that connect back to size and structure. The next inward step moves into the surface layer itself, where heating, crust formation, and cracking decide how gas and dust are released in the first place. With rotation as the controlling rhythm, the next inward region is the surface layer, the boundary where sunlight becomes heat, where heat becomes phase change, and where phase change becomes escaping material. The surface is not a simple exposed ice plane. It is typically a mixed porous layer of dust organics and ices altered by radiation and impacts over time. In this region, the focus stays with the physics of that near-surface layer, how it warms, how it insulates, how it cracks, and how it channels gas and dust into space. This is where an object can appear to do something rarely seen because small changes in permeability and structure can produce disproportionate changes in observable behavior. Sunlight deposits energy into the uppermost grains. A surface patch warms depending on its albedo and on the angle of sunlight. Darker surfaces absorb more light and warm more. Brighter surfaces reflect more and warm less. But even a dark surface does not necessarily imply rapid sublimation because the heat must reach volatile layers. The near-surface layer can act as an insulating blanket. Dust left behind by past sublimation can accumulate into a mantle. A mantle can be porous, allowing gas to pass, or it can become compacted and sealed, restricting gas flow. If the mantle is thick enough, it can delay activity by preventing heat from reaching underlying ice and by limiting how quickly gas can escape once produced. Heat penetrates by conduction. The rate depends on thermal conductivity and on thermal inertia. In a porous mixture, thermal conductivity can be low because contact between grains is limited. This makes the surface highly insulating. The depth to which the daily temperature cycle penetrates is set by rotation period and thermal properties. A fast rotation produces a shallow thermal skin depth. A slow rotation allows deeper penetration over the longer timescale of the inward approach. There is also a seasonal skin depth tied to the changing average sunlight with distance. This longer-term warming can penetrate more deeply and can gradually shift the location where volatiles begin to sublimate. Different volatiles respond at different temperatures. Water ice is abundant in many comets, but requires relatively strong heating to sublimate vigorously. Carbon dioxide and carbon monoxide can sublimate at lower temperatures and can drive activity farther out. If 3I Atlas shows activity at large, solar distances, supervolatile sublimation is a plausible driver. Yet even if supervolatile ices exist, they must be accessible. If they are buried under an insulating mantle, they may remain trapped. If fractures provide pathways, they may vent. Therefore, the onset of activity is not only a chemical question. It is a structural question about the near surface. Cracking is central to that structure. Thermal stress arises when surface layers expand in warmth and contract in cold. Repeated cycles can create fractures. These fractures can increase permeability and allow gas to escape more efficiently. They can also expose fresh material. Fresh material can include more volatile, rich ice that had been protected below the surface. Exposure can produce a change in brightness, not because the nucleus changes size, but because new surfaces and new dust are released. In a low-gravity environment, even small fractures can lead to collapses and slumps, releasing dust into space. Pressure buildup beneath a mantle can also lead to sudden venting. If heat reaches a volatile layer and sublimation begins, gas pressure rises. If the mantle is permeable, gas diffuses out gradually. If it is sealed, pressure can build until it exceeds the strength of the overlying material. Then a rupture can occur, releasing gas and dust in an outburst. Outbursts can cause rapid brightening and changes in coma morphology. Some outbursts are small and subtle, detectable only in precise photometry. Others are dramatic. In either case, they are not rare in cometary physics, but they are rarely observed in detail at large distance because of faintness and limited monitoring. An interstellar object that is tracked well could therefore show a rare observational record of an outburst in a context where it is usually missed. The near surface can also contain trapped gases in specific ice structures. Amorphous ice is a disordered form of water ice that can trap gases within its matrix. When amorphous ice warms enough, it can transition to crystalline ice, releasing trapped gases. This crystallization also releases latent heat, which can accelerate further change. This mechanism has been proposed as a contributor to distant activity in comets. Clathrate hydrates, cage-like structures of water ice that trap other molecules, can also release gases when conditions change. If 3I Atlas exhibits activity onset farther out than typical water-driven comets, these trapped gas mechanisms are plausible within standard models. They are difficult to confirm directly, but they offer a structured explanation, a surface that has preserved amorphous ice or clathrates can release gas in a way that does not depend solely on near-surface water sublimation. Dust behavior in the near surface is governed by cohesion and by gas drag. Dust grains can stick together due to microscopic forces and due to ice acting as cement. When sublimation occurs, it can weaken the cementing freeing grains. Gas flowing upward can then drag grains into space. In low gravity, the threshold for lifting is lower than on a larger body. Therefore, even weak gas production can produce a measurable dust coma if grains are available, and cohesion is not too strong. This can create a situation where brightness and coma are dust-dominated, while gas remains difficult to detect spectroscopically. Such a decoupling can make the object appear unusual, because brightness suggests strong activity while gas lines remain absent. The near-surface explanation is that dust release efficiency can be high even when gas production is modest. Surface evolution can also create feedback. If dust is lifted and then falls back, it can redeposit, thickening the mantle in some regions and thinning it in others. If jets are localized, they can erode pits and expose deeper layers, sustaining activity in those regions. If the spin axis causes certain regions to receive more sunlight, those regions can evolve more quickly, leading to seasonal activity patterns. Over time, the distribution of active regions can shift, changing the coma's shape and the direction of any recoil force. These changes can manifest as variability in brightness and as changes in non-gravitational acceleration components. Again, the physics is standard. The rarity lies in the chance to observe it well in an object that may not behave like a typical returning comet. Radiation processing of the surface adds another dimension. Over long time, ultraviolet light and cosmic rays can darken and chemically alter surface layers, creating complex organic residues. Such residues can form a crust that is mechanically stronger than fresh ice-dust mixtures, increasing resistance to gas escape. If 3I Atlas has traveled in interstellar space for a long time, its surface may carry such a processed layer. If so, initial heating might not immediately produce strong activity. Activity might begin only after cracking and fragmentation open pathways. This could produce a delayed and then sudden onset, which might appear rare compared to smoother activation in some solar system comets. Yet it would still be a natural consequence of surface processing and mechanical failure. In this region, the surface is treated as a working boundary layer. Sunlight and rotation impose thermal cycles. Thermal cycles create stress and cracks. Heat retches volatile layers with a delay set by insulation. Gas builds and escapes through pores or ruptures. Dust lifts when drag exceeds cohesion. The observable coma and brightness respond. 3I Atlas can appear to do something rarely seen if this chain produces activity onset at an unusual distance, if it produces outbursts that are caught in real time by monitoring, or if it produces a pattern where dust and gas diagnostics do not align in simple ways. The description remains calm and bounded. These outcomes arise from the ordinary behavior of porous materials and volatile ices under changing heat input in a low-gravity environment. From the near surface as a structural boundary, the next inward region is the microscale, where the same story is told in smaller units molecules, leaving an ice surface gas moving through pores, grains detaching from contacts, and sunlight interacting with particles. These processes are not a separate world. They are the base mechanisms that set the parameters used in higher-level interpretations of brightness coma shape and non-gravitational acceleration. In this region, the focus stays with sublimation kinetics, gas transport regimes, dust-lifting physics, scattering behavior, and the simple photochemistry that governs coma composition as it moves away from the nucleus. Sublimation begins at an ice interface. At a given temperature, molecules in a solid have a distribution of energies. Some fraction has enough energy to escape the surface into the gas phase. The rate of escape increases steeply with temperature because the vapor pressure rises rapidly. In vacuum, molecules that escape are not contained, so sublimation proceeds as long as energy is supplied. The energy supply comes from absorbed sunlight and from heat conducted from warmer layers. Sublimation also consumes energy as latent heat, cooling the surface and moderating temperature rise. This creates a balance. Heating raises temperature and increases sublimation. Sublimation cools and reduces temperature, and the system settles into a rate set by the incoming energy and the ability of gas to escape. Gas escape is controlled by pore structure. In very low-pressure environments, gas flow through pores often occurs in a regime where collisions with pore walls dominate over collisions between molecules. This regime makes the geometry of the pore network decisive. Narrow pores, sharp bends, and rough surfaces increase resistance. The result is that two surfaces with the same volatile content can produce different outgassing rates depending on their microstructure. Microstructure can change over time. Sublimation can enlarge pores by removing ice. Dust can clog pores by settling. Recondensation can narrow pores by depositing ice in colder regions. Therefore, permeability is not fixed. It evolves, and that evolution can produce variability in activity without any change in bulk composition. The gas that exits into vacuum expands rapidly. Its outflow speed depends on temperature and molecular mass. Lighter molecules move faster. The outflow can be diffuse if it emerges through many pores, or collimated if it emerges through a vent or crack. Collimation matters because it determines thrust efficiency. A collimated jet produces a net force in a particular direction. A diffuse flow produces more cancellation between directions. Therefore, the microscale path from sublimation layer to exit geometry affects the macroscopic non-gravitational acceleration. A small change in vent shape can change net thrust while leaving total mass loss similar. This can produce a mismatch between brightness-based activity measures and dynamical measures. Dust lifting is governed by a balance between gas drag gravity and cohesion. On a small body, gravity is weak. Cohesion can dominate. Cohesion comes from microscopic contact forces and from any cementing by ice or organics. Gas drag depends on gas density and flow speed near the surface. If gas flow is weak, drag may not overcome cohesion and dust remains. If gas flow strengthens, dust can be lifted. The size distribution of lifted grains depends on how drag scales with grain size and on how cohesion scales with contact area. Small grains can be strongly cohesive relative to their weight. Larger grains have more mass and may be harder to lift. Yet contact geometry can make certain grain sizes easier than others. The resulting dust population in the coma can change with time as the surface evolves and as gas flow changes. Once dust grains are in the coma, sunlight acts on them. Radiation pressure pushes them away from the sun with stronger acceleration for smaller grains. This sorting effect can change the grain size distribution near the nucleus versus farther out. Fine grains can be swept away quickly, leaving larger grains closer in. This affects the brightness profile of the coma. It also affects color because scattering depends on grain size. Therefore, the observed color and brightness can evolve as grains move, even if the nucleus produces a steady outflow. In addition, grains can fragment, especially if they are aggregates. Aggregates are clusters of smaller grains. They can break under thermal stress or under collisions within the coma, producing more fine grains and altering scattering properties. This can create changes in brightness and color that are not tied to changes in production rate. Scattering itself is sensitive to microphysics. The way a particle scatters light depends on its size relative to wavelength, its shape, and its refractive index, which is tied to composition. Many comet dust grains are irregular and porous. Such grains can produce strong forward scattering. Forward scattering can make the coma appear much brighter at certain phase angles. This effect can be large even for modest dust quantities. Therefore, an object can appear to brighten strongly without a corresponding increase in dust production, simply because geometry brings the observer into a configuration where forward scattering is enhanced. The microphysical reason is the angular distribution of scattered light produced by irregular particles, and the macroscopic result is a brightness surge. Gas in the coma undergoes photochemistry. Sunlight can break molecules apart, producing radicals and fragments. It can also ionize molecules. The lifetimes of different species depend on solar distance and on molecular properties. Parent molecules released from the nucleus may not be the species most easily observed. Instead, observers often detect daughter species that fluoresce efficiently. This means that observed spectra reflect both composition and processing. If a gas species is absent in spectra, it might be absent in the coma, or it might be present but transformed into other species, or it might be present at a level below detection. Therefore, microphysical lifetimes and transformation pathways become part of the uncertainty in translating spectra into nucleus composition. Electrostatic charging can affect the smallest dust grains. Ultraviolet light can eject electrons from grain surfaces, leaving grains positively charged. The solar wind can add or remove charge. Charged grains can respond to electric and magnetic fields in the solar wind, especially if they are very small. This can shape fine dust distributions and interact with ion flows. For most of the dust that dominates optical brightness, radiation pressure remains the main driver. Still, charging matters as part of the microphysics that can create subtle structures and variability in the coma. At the surface itself, microscale chemical processing can alter mechanical and thermal properties. Radiation can produce complex organic residues that darken material and change its ability to conduct heat. It can also increase brittleness, making crusts more prone to cracking. A darkened crust absorbs more sunlight, potentially increasing near-surface heating. But if the crust is thick and porous, it can still insulate deeper layers. These microphysical changes can accumulate during long exposures to radiation in deep space. For an interstellar visitor, this exposure may be long, and the surface may be strongly processed. The result can be a surface that behaves differently from a typical returning solar system comet, not because it is made of unknown substances, but because of the extent and duration of processing. Doing something astronomers rarely see in this micro-scale region can therefore be framed as a rare combination of microphysical parameters manifesting in observable ways. A particular pore structure can produce gas-rich outflow with little dust. A particular grain population can produce strong forward scattering and unusual brightness behavior. A processed surface layer can delay activity and then produce abrupt venting when cracks open. A volatile mixture can shift activity onset to larger distances. Each outcome is grounded in known microphysics, yet the space of possible combinations is large, and only a small fraction are observed clearly, because few objects are monitored closely at the faint end. This region ends by anchoring the entire outward-to-inward path in the smallest mechanisms that still matter for observation. Molecules leave ice when warmed. Gas finds pathways through pores. Dust lifts when drag overcomes cohesion. Light scatters from grains according to size and structure. Molecules transform under sunlight. These microphysical steps generate the macroscopic signals, coma, brightness, spectral features, and small accelerations. The final step inward will state what is most firmly known and what remains uncertain, using this chain to keep the uncertainty specific rather than vague. At the innermost boundary of this outward-to-inward path, the task is to state what can be held with the greatest stability about 3I Atlas and what remains open in ways that are specific and bounded. The object may be described as doing something astronomers rarely see, but the rare aspect must be kept inside evidence. Rarity can be real in the statistical record and still be explained by ordinary mechanisms. This section therefore gathers the strongest constraint classes and places them beside the most persistent uncertainties, without turning uncertainty into speculation and without turning constraint into certainty beyond what measurement supports. The most stable foundation is astrometry. The object's position on the sky at known times reported across multiple observatories constrains its track. As the time baseline grows, the orbit solution becomes more stable. From that orbit, the object's trajectory can be expressed in orbital elements and in predicted future positions with quantified uncertainty. This remains true regardless of whether the object is active or inactive, because even activity-related accelerations are diagnosed through their imprint on the astrometric residuals. In other words, the motion is the anchor. The orbit is not a story. It is a mathematical compression of the motion with known limits. From this anchor, classification can be addressed. Interstellar classification, when robust, is an orbital energy statement. It depends on whether the inbound barycentric orbit is unbound with high confidence after accounting for planetary perturbations and for the quality of astrometric data. If the eccentricity remains above 1 by an amount larger than uncertainties and the inferred asymptotic speed is clearly positive, the interstellar label becomes strong. If the orbit is near the boundary, classification remains sensitive and requires more data and careful handling of systematics and non-gravitational terms. In either case, classification does not provide a parent star system. It provides the dynamical state bound or unbound with uncertainty. The origin remains open because backward tracing through the galaxy amplifies uncertainties, and because stellar motions and past encounters complicate the path. Photometry provides the next stable class of evidence, but it carries more interpretive dependence. Brightness measurements across time establish a light curve and a brightness evolution. These data can show whether brightness trends align with distance-driven expectations or whether additional factors are needed. They can show whether periodicity exists that suggests rotation. They can show whether variability is smooth or irregular. They can show how color changes with time if multi-band data are available. Yet photometry alone does not uniquely determine size because albedo is unknown, and it does not uniquely determine activity because phase angle scattering and background contamination can mimic intrinsic changes. Therefore, the most stable photometric statements are comparative. The object brightens or fades by a measured amount over a measured interval. It shows or does not show periodic variability above a measured threshold. Its colors fall within a measured range. Spectral and multi-wavelength data, when available, sharpen certain questions. A continuum slope constrains scattering properties of surface or dust. Emission lines, if detected, confirm gas and identify species or at least classes. Non-detections provide upper limits on production rates for targeted species. Thermal infrared detections, if obtained, can constrain size and albedo together. Radio searches can constrain certain volatiles, such as carbon monoxide. Yet these measurements are often sparse for faint objects, and their absence is not proof of absence. Therefore, composition remains a layered uncertainty unless clear detections exist. The safest statements are those tied directly to detections and to reported sensitivity limits. The coma, if detected, provides the strongest evidence for ongoing mass loss. Extension relative to stars, aperture-dependent brightness growth, and morphological features support an envelope of dust and possibly gas. The onset distance of coma signatures, if well measured, constrains which volatiles or thermal processes are likely to be active, but it does not uniquely identify them. A coma can be dust-rich and gas-poor in detectability, or gas-rich and dust-poor in brightness. The coma's presence also complicates astrometry by shifting centroids, and it complicates size inference by adding scattering area. Therefore, the coma is both a signal and a source of bias. The most stable statement is whether extension is repeatedly detected and how it evolves. Non-gravitational deviations, if they are robust, are another strong constraint because they tie directly to motion. A persistent residual pattern reduced by adding non-gravitational terms suggests an additional acceleration beyond gravity-only modeling. The fitted acceleration components with uncertainties are measurable outputs. Interpreting them requires caution because of coma-induced centroid bias trailing and model dependence on distance scaling. Still, if the effect persists across data selections and observing systems, it implies that a physical force is acting most plausibly, outgassing recoil and possibly radiation pressure if size and mass constraints allow. This remains within standard physics. It becomes rare mainly in an observational sense when the effect is detectable at large distance, or when it is well measured for an object that is faint and hard to track. Global physical properties remain uncertain in specific ways. Size is uncertain because albedo is uncertain and because coma contribution can inflate brightness. Shape is uncertain because light curve amplitude depends on viewing geometry and coma masking. Mass is uncertain because it is not directly measured, and because dynamical inference of mass requires thrust estimates that usually depend on gas production rates and jet geometry. Density is uncertain because it depends on both mass and size. Rotation state can be uncertain because of aliasing in time sampling, because activity can modulate brightness, and because tumbling can produce complex signals. These uncertainties are not failures. They are boundaries set by available measurements. The phrase "doing something astronomers rarely see" can therefore be translated into a careful statement of what is rare in the present record. It can be rare that an object appears unbound and is observed with enough coverage to refine its orbit strongly. It can be rare that subtle non-gravitational deviations are measurable early, either because the object is small, active, or exceptionally well tracked. It can be rare that activity onset is seen at large distance in a way that can be followed continuously. It can be rare that brightness behavior is strongly influenced by forward scattering in a documented geometry. It can be rare that rotation signatures are resolved cleanly in a faint interstellar candidate. Each of these is a rarity of circumstance and data set as much as a rarity of object physics. What remains open is stated as concrete questions rather than broad mystery. Which volatiles, if any, dominate the activity, and at what production rates? How much of the brightness is nucleus versus dust, and therefore what the nucleus size range truly is? Whether the rotation is simple or complex, and whether it evolves measurably under outgassing torque. Whether the non-gravitational acceleration, if present, is stable in direction and magnitude, or changes in a way that indicates localized jets. How porous and mechanically weak the body is, which affects both mass loss efficiency and stability. These are the interior edge questions that can be narrowed only with additional data, and even then may remain bounded rather than solved. The innermost point of this script is that the strongest description of 3I Atlas is a layered set of constraints: motion first, then light, then wavelength, then coma, then dynamics beyond gravity, then cautious physical bounds. Within those layers, the object can be rare in the observed record, while still being ordinary in mechanism. The solar system provides gravity, light, and plasma. The object provides material structure and volatile content. The interaction produces measurable signals. The rare part is that the signals are captured well enough, early enough, and consistently enough to be studied across the full chain from outer context to microphysics.